So this is called limits at infinity, and you might remember the last one was called infinite limits. And you would probably be like, well, these sound like the same thing, but they're actually not. So limits at infinity mean as x approaches infinity. In other words, as my x-axis is getting way that way toward infinity, what's happening with the y values? And infinite limits say as x approaches some number, what's happening with the y values. Like maybe in this case, see how these y values are getting close to negative infinity as x is approaching this number right here. So as I approach that number on the x-axis, my y values are getting down here closer and closer to negative infinity. Limits at infinity would say as my x-axis pushes toward infinity, what happens to the y values? So this would be a limit at infinity, or some people like to call these horizontal asymptotes. So horizontal asymptotes, you know, like you can see there could be a horizontal asymptote right here. Sometimes population growth will level off or things like that. That's what a limit at infinity is all about. So here's the first rule with rational functions. When the degree of the numerator is greater than the degree of the denominator, in other words, the highest exponent on the top is bigger than the highest exponent on the bottom, then your limit as x approaches infinity, your y values will also approach infinity. So an example of that might be y equals x squared over x minus 3. So for this rational function, the limit at infinity, or in other words, the limit as x approaches infinity, is also infinity for this function right here. And when the degree is smaller on the numerator than it is on the denominator, in other words, the degree of the top is smaller than the degree of the bottom, like maybe this one right here, y equals, let's say, 1 over x. See that the highest exponent down here is a 1, and the highest exponent up here is a 0. So this rational function, the limit as x approaches infinity, is 0. And a picture of 1 over x, let's kind of plot that over here and get a mental idea of what 1 over x actually looks like. So we know there's a vertical asymptote at 0. When x is 0, the bottom is 0, so this right here is the vertical asymptote of the graph. I just said this has a horizontal asymptote of 0. This means a horizontal, or in other words, y equals 0 is a horizontal asymptote. So this is a horizontal one, and this is a vertical one. And we know that we can just kind of pick some values here, like let's pick some easy ones, like 1. When x is 1, y equals 1 over 1. So this is on the graph. What if I pick 10? Y would be 1 over 10, so that would be way out here. If I picked 1/10, 1 divided by 1/10 is, flip the bottom and multiply, that's 10 over 1, so that's way up here. So we can see that right here, the limit as x approaches infinity, as my x values are getting this way, the y values approach 0. And as the limit as x approaches 0, this was yesterday's lesson of 1 over x, here's my function. This is positive infinity. So we covered that yesterday. This is an infinite limit. This is a limit at infinity. That's the difference. And over here on the left side, if I picked like -1, I would find out that 1 divided by -1 is -1. And I'd see that this is going to be a mirror image of that if you picked more numbers. Of course, this drawing's not perfect, but anyway, we see that the limit as x approaches 0, so this would be an infinite limit of 1 over x is negative infinity. See, as my x values are pushing towards 0, my y values are going down to negative infinity. But as my x's approach negative infinity, in other words, as my x values are going this way, my y values are coming up here to 0. Okay, so that is what limits at infinity are all about. And that's only when the degree of the numerator is smaller than the degree of the denominator do you get a limit of 0, which means a horizontal asymptote is 0. Now there's one more rule, and that's when the degree of the top is the same as the degree of the bottom. When this happens, you take the ratio of the leading coefficients. So you probably need an example to see what I'm talking about. Let's say I have f of x is x cubed plus 2x plus 6 all over x squared minus 3x cubed plus 9. Now, I picked this example specifically to talk about, most people would think the leading coefficient is this coefficient and this coefficient, and that's a common mistake. The leading coefficients are if it's written in the correct order, the leading coefficients. In other words, highest exponent down to lowest exponent, but you see this one's out of order. So my ratio should be 1 over negative 3. So the limit as x approaches infinity is negative 1/3 for this function. And that's because you take the ratio of the leading coefficients, in other words, find both the highest powers, and when they're the same, see the degree of the numerator is is equal to the degree of the denominator. In other words, these are the same number on the power. You take the ratio of these coefficients, or in other words, make these a fraction. So 1 over negative 3. So this would have a horizontal asymptote down here. Okay. And that's the only rule for that. So I'm going to pause this and put up some examples. And here's 3 examples, and you could pause your screen, work these yourself, and see if you get the right answer, and then unpause it and watch me work it. So remember the 3 rules we talked about. When the top's bigger than the bottom, your limit is going to be infinity. When the bottom's bigger than the top, your limit's going to be 0, and when the bottom and the top are equal in degree, your limit will be the ratio of the leading coefficients. So we can see on this example, the degree of the top, which is a 2, is greater than the degree of the bottom, which is a 1. So since the degree of the top's bigger, we say this is infinity. So these go really quick today. Here, the denominator is greater in degree, so we say this one is 0. Here, the degrees are the same, so we will use, since we're careful to notice that these are written in descending order, these are written in descending order, so these are indeed the leading coefficients right here, so there's your answer, 3/5. You got to make sure that, as in the last example, these aren't written out of order. So you take the leading coefficients. And that's it for limits at infinity.